Welcome to class today. Today we'll be looking at section 2.5, linear functions and models. I hope that you're finding chapter 2 to be a little bit more manageable, the amount of material that's within each section. It seems like it does slow up just a little bit in chapter 2 for us. So today we're going to be looking at some word problems, but they're very easy word problems. So I think you'll find this to be something you can be very successful with. Okay, specifically in this section, we're going to be looking at linear functions, and with linear functions, okay, in this section, we're going to be looking at linear functions. The linear functions are those that are going to be of the form ax plus b, or more familiar to us would be the mx plus b. So basically, we're just talking about a line, except we're going to change the notation. So instead of just being an equation, it's going to be a function. So we'll have an f of x here in the place of the y. And typically our m is going to be represented by this a here. So that's kind of what we're talking about with this. So keep in mind that you're still going to have a y-intercept and you're going to have a slope for each of these linear functions. Okay. So first of all, we need to be able to identify what is a linear function. So in order for it to be a linear function, it needs to be able to be put in this form, and x can only be to the first power, which means we can't have an x squared, we can't have an x cubed, we can't have a square root, any of those things, and it be a line. So this one we could put in the form ax plus b just by moving it around. So this one would be linear. Here, if I were to distribute this, then I could move it around. And so this would be in the form mx plus b. So that one would be linear as well. Here, if I distribute, I see that I have a squared term, and I can't have a squared term on a linear function. So this one would not be a linear function. This one, I can split it up. I would have 1/4 minus 5/4 x. Move this around. And so then I have it in the form mx plus b. So that one would be linear as well. So the only one that's not linear is c here, and this will be quadratic. Okay, here you need to be able to graph linear functions. That's just graphing a line. So just think of it as y equals, and you've got this this function here. As far as making a table, when you make a table and you're doing the functions, you just put, instead of x, y, you put x, f of x. Still going to look at some of the similar values here. Okay, so if my function is 3x plus 2, then I'm going to put negative 2 in here. So that'll be negative 6 plus 2 would be negative 4. If I put negative 1 in, I'll have negative 3 plus 2 would be negative 1. If I put 0 in, I'll have 2. If I put 1 in, I'm going to have 5. And if I put 2 in, I'm going to have, that would be 6 plus 2 would be 8. Okay, so then I can plot my points. And again, I apologize for not being able to draw nice straight lines here. So negative 2, negative 4, negative 1, negative 1, 0, 2, 1, 5, and 2, 8 is going to be up here. And if we connect these, which is going to be hard for me to do in a nice straight line, but if we connect these in a straight line, then that's the line that represents our function. Obviously, you can do these on your calculator as well, so that's fine. Okay, so if you keep in mind that slope and average rate of change are the same thing, it's going to make this section a whole lot easier for you. So if you're asked to find the rate of change of anything, that's just another way of asking for you to find the slope of the equation. So that's really all this section is doing, is connecting those two, slope and rate of change. So we have our slope formula in terms of the y's, and if you go to the function notation, then it's just going to change each of these y's into an f of x for us. And that's really all that it's telling us here. Okay, so if we're looking at a regular equation here, which in function notation is going to look something like this, then m is going to be, like we said, your slope, but it's also going to be your rate of change. So in a word problem, when it tells how something is changing, that's your slope. The other part you need to recognize here is your y-intercept. That's always going to be your initial quantity. So however much you're starting with is what your initial quantity is going to be. Because if you think about it on a y-intercept, let's say this is your y-intercept here, that's the amount that you have at 0. And so that's what an initial quantity is. And so your y-intercept will always be your initial quantity. So when you're asked to write a model, you're just going to go back to this notation here, and you're going to plug in your slope, which is your rate of change, and your b, which is your initial or starting quantity. And then you're going to have your linear model that you need. Okay, here's an example. A dam is built on a river to create a reservoir. The water level F of t in the reservoir at time t is given by this function, where t is the number of years. I will say keep track of your units here since the dam was constructed, and F of t is measured in feet. Okay, so we're talking about years and feet here. I'm not so concerned about sketching the graphs of these because all you really need to do for this is to go back and put it in your calculator, and you might have to adjust your window, but you could pretty easily get a graph of that. So I'm not going to go through that part. What is the slope of the graph? So if I've translated this into this equation here, then I can clearly see this is my m, because this is my mx plus b format. So the slope is going to be 4.5. And then what is the rate? We said that the rate something is changing is equal to the slope. So I'm going to give the 4.5, but I do want to give my units with this. So this is changing at 4.5, and this is feet per year. Okay, so when you do this, because slope is your change in the y's over the change in the x's, you want to use the units for the y's, and you're going to divide that by the units for the x's. Okay, so in this case, my x was represented by a t, so that would be the years, and the f of t is like the y, and so that's going to be the feet. Okay, this is a graph just showing you what if you put that equation in your calculator, this is what you would have had. Notice this has an intercept of 28, so if you just try to do your standard window, you're going to be way down here and you're not going to see your graph, so you would have to adjust your window on that. Okay, so you can have positive slopes, which mean positive rate of change, or it means it's increasing, or you can have a negative rate of change, which it means you have a negative slope and it means it's decreasing. So on this particular one, it's an increasing slope, so the rate of change is increasing, and you've got your y units over your x units, so it's going to be gallons over minutes. So gallons per minute with that. Anytime you have a graph, you can always count rise over run to get your slope. So my rise here would be 6 units and my run would be 3 units. So I'd get a slope of 6 over 3. Okay, this one you can see the graph is falling. It has a negative slope. So that means it has a negative rate of change. And as far as the value, if I do rise over run, this one I'm actually going to fall 3 units. And then I'm going to run 100 units. So if I simplify that, I get negative 0.03. And as far as the units goes, my y units go on top and my x units go on the bottom. Okay, water is being pumped into a swimming pool at the rate of 5 gallons per minute. Initially, the pool contains 200 gallons of water. Find a linear function v that models the volume of water in the pool at any time t. I will say when we're writing these linear models, it's important to use the correct notation for it. So we're going to essentially start with y equals mx plus b, but we're going to substitute and change this as needed. So we're told that we want to do the linear function v, and we want to do that in terms of the variable t. So this is, instead of y, my function notation is going to be v of t. So I'm going to be finding the volume in terms of the variable t. Okay, I need to find my slope, which is my rate of change. So if I look up here, it's the water's being pumped into the swimming pool at the rate of 5 gallons per minute. So that is going to be my slope or my m in the equation. So I'm going to put 5. It's based on the variable time, so this is going to be a t. And then my b is my initial quantity. So we know that the pool initially had 200 gallons of water before they started pumping it into it. So that's where the 200 is going to go. So this is the linear model or the linear function that they're asking us to find. So we base it off of this, but we do need to adapt it notationally and find our slope and our y-intercept in order for this to be an accurate function for us. So working with the same problem here, we found that our model was, V of t equals 5t plus 200. So on this one, the pool has a capacity of 600 gallons, so that's telling me my volume. So I'm going to do 600 here for the volume. And then I'll just solve for the time. So I'm going to have 5t equals 400. Divide by 5, and t is 80. And so that's going to be 80 minutes. That's what my time is being measured in. And that's going to be my answer for part B. Okay, here's one where we're going to be writing a model to represent the height of the trim board. So we have placed the staircase in a coordinate plane with the origin at the bottom left corner. So here's our origin. The red line in the figure is the edge of the trim board of a staircase. Okay, so we want to find the linear function h that models the height of the trim board above the floor. Okay, so what we have is we have our height is our dependent variable here, and our x, the distance we are away, is going to be our independent variable. So when we start with our model y equals mx plus b, we're going to have h, and since this is just represented as x, we're going to have h of x. We need to figure out our slope, and we need to figure out our y-intercept. The y-intercept is pretty clear. We can actually just look at our graph here and see we have a y-intercept of 8. We need to figure out the slope, and they don't really specify a rate of change, but they do give us 2 points to work with. So we're going to use those 2 points and find our slope. So our 2 points were 1216 and 3632. And you could have actually used this intercept as a third point if you wanted to choose any of the two. 2 of the 3 is all you really need. So here if we do y2 minus y1 over x2 minus x1, I'm going to have 16 over 24. 8 goes into both of these. 8 goes into 16 2 times. 8 goes into 24 3 times. So I'm going to have a slope of 2/3 or 2/3. Okay, so our 2/3 is going to go here. And this is going to be our linear function for this problem. Okay, part B here, if the space available to build a staircase is 11 feet wide, how high does the staircase reach? Well, we found in part A that our model was h of x equals 2/3 x plus 8. Okay, so we want to find out how high does the staircase reach. So we're going to be finding the height here, and we need to put in our 11 for our x. So we're going to have 2/3 times 11 plus 8. When we simplify that, we're going to, actually, I'm going to back up here because this is what I just did is a very common mistake, and some of you may have caught this. We've got 11 feet, but our model was built off of inches, so be really careful about units in this problem. So if I'm going to convert 11 feet to inches, I need to multiply it by 12, so that's going to be 132 inches. So I'm going to go back and change this to 132, and then I'm going to simplify that, and I'm going to have 96 inches. So when I'm 11 feet out from the starting point here on the stairs, the height of the stair Okay, for John and Mary on this problem, they're driving westward along I-76 at constant speeds. The graphs in the figure show the distance in miles that they have traveled from Philadelphia at time x in hours, where x equals 0 corresponds to noon. So this is going to be noon here. Note that John has already traveled 150 miles, so he's starting out already 150 miles further along the route than Mary is based on this. So what we need to do is actually identify a few points that we can use along the way. Here for Mary, I'm going to use the point 0, 0, and then I'm also going to use the point 7, 500. For John, I'm going to use the point 0, 150 here. And then we want to find another point where it crosses and it's easy to read. And so this point here looks like it's pretty easy to read. So we'll use the point 1, 200. So these are not exact when you have this large of a scale on the y-axis. So we'll just have to do the best we can with it. Part A asks us to find the speeds. So speeds or rate of change is its slope. So we need to figure out the slope for each of these. So for John, we said for John, we're going to use the points 0, 150 and the point 1, 200. Okay, so our slope for him is going to be 200 minus 150 over 1 minus 0. So that's going to be 50 for the slope for John, and that's going to be 50 miles per hour. For Mary, we're going to have the point 0, 0 and the point 7, 500. So our slope is going to be 500 minus 0 over 7 minus 0. So 500 over 7. And so that's approximately 71 miles per hour. And again, depending on how you read these points, these could be off by a little bit and it still be acceptable. Who is traveling faster? Obviously, Mary's traveling faster because she has a steeper slope, and that shows up as far as just looking at the graph. It's got a steeper rise over run. So even though John starts out ahead of Mary, Mary's able to overtake John at some point here. Okay, find the functions that model the distances that John and Mary have traveled as a function of x. So for John, we're going to go back to our y equals mx plus b. This one we're talking about distance in terms of the variable x. So we're going to use d of x equals 50 for the slope that we just found, x for our variable, and then the y-intercept for John is here at 150. So this is the model for John. If we look at for Mary, we're still going to use our d of x. Mary's rate of change or slope was 71. So we're going to use 71x, and then her y-intercept was 0. So you could either put plus 0 or you could leave it like it is. So this would be the model for Mary. This would be the model for John. Okay, part C, how far will John and Mary have traveled at 5 p.m.? So this would be when x equals 5. So we're going to go, I'm kind of running out of space here, but C, I'm going to plug in 5 to each of the equations. So 50 times 5 plus 150 is going to be 400 miles. Is going to be the distance that that John has traveled at 5 o'clock, which is after 5 hours. If we look at Mary, okay, so this one's Mary. This one was John. Okay, so for Mary, we're going to take the 71 and multiply it by 5. And so with that, we're going to have 355 miles. If we look at our graph, that does look right because here at 5 o'clock, John is still a little further than Mary. So he has traveled just a little bit further than Mary. So that would make sense. For what time period is Mary behind John? We can see here that they overtake each other where they intersect. And so Mary's behind John for all of this time. So for part D, we have a couple options. One, we could actually set these equal to each other and solve. The problem with doing that is this scale is so large that we may not get a very exact answer. So I would just say look here at the graph and see when Mary's able to overtake John. So it looks like about 6 o'clock. So after 6 o'clock is when she's able to overtake him. So Mary's behind John up until 6 o'clock, and then after that she's going to be ahead of John. Okay, here's some others that I would like for you to try. So I've included the answers on the next slide. So if you'll try this on your own, and then take a look at what your answers should be. Okay, on this one, we've got the koi pond is filled with a garden hose filled from a garden hose at the rate of 10 gallons per minute. So that's going to be my slope. Initially, the pond contains 300 gallons, so that's going to be my y-intercept. So when I use this, I need to make sure that I use v as my function notation in terms of the variable t. And so I end up with this for my slope and this for my y-intercept. If a pond has a capacity of 1,300 gallons, how long does it take to completely fill the pond? If we look at this, the capacity is its volume. So basically it's telling me that the volume is 1,300 gallons. So I'm going to put the 1,300 in for the volume and solve it for t. So it just becomes a linear equation that we'll solve. And we get that after 100 minutes, it'll have the pond will have a capacity of 1,300 gallons. Here's one very similar to the one that we just got through completing about the travels. So take a minute and try this one. Okay, looking at this, part A, use the graph to decide which person's traveling faster. Jari has a slightly steeper slope, so it's going to be Jari that's traveling the fastest. Part B, find the speed in miles per hour at which each of them is driving. So we've got pretty clear points identified in this problem. So use the ones that are identified. This would be 0, 0. This would be 0, 10, along with these other points here. So you're going to calculate the slope of each of those. So the slope for Jade is going to end up being 1. You need to be careful here with your units because it asks for it in miles per hour. So to convert miles per minute to miles per hour, I need to multiply it by 60 minutes per hour so that our minutes will cancel doing these conversion factors, and I'll end up with 60 miles per hour for Jade. For Jari, if I set this up, calculate, I get 7/6 miles per minute, convert that by multiplying by 60, and I get 70 miles per hour for that. So these are the speeds that they're traveling. One's traveling 60 miles per hour and Jari's traveling 70 miles per hour. Okay. Find the functions f and g that model the distances that Jade and Jari travel as functions of t. And this wants it in minutes. So it's going back and forth between hours and minutes. So if I want this in terms of minutes, then I actually want to use the slope here before it's converted. So for Jade, she had a slope of 1 and a y-intercept of 10. Jari had a slope of 7/6 and a y-intercept of 0. So these are the two models that we should have found in terms of the variable t. Okay, here's another one for you to try. Okay, if we look at the sketch of the graph, again, use your calculator and that's fine. This one has a y-intercept of 200, so you're definitely going to have to change your y max on your screen in order to be able to see the graph. So if you're bringing up a blank screen, it's because your window has to be adjusted. What's the slope of the graph? Put this in mx plus b form, so that just means kind of moving it around a bit. Our slope is going to be 32. And at what rate is the amount of ore changing? So the rate of change is the same thing as the slope. I do want you to put your units with it when you talk about rate of change, though. So this one was in thousands of tons, and then that's going to be per year. So again, put your y units over your x units. Okay, the amount of trash in a county landfill is modeled by this function where X is the number of years since 1996. T is measured in thousands of tons. At what rate is the amount of trash in the landfill increasing per year? So try this one. Okay, so if we look at this, this is actually pretty simple. Our slope is our rate of change. So there's our slope, 120. So it's 120, and our units is going to be thousands of tons per year with that. Okay, this example here tends to give people a little bit of problem just because it's hard to set up the ordered pairs. So you're asked to find a linear function C that models the cost of driving X miles per month. We need to think about what's your independent and what's your dependent variable. So the way this is described here, we are told that the driving cost depends on the number of miles driven. Okay, so the cost depends on the miles. So that means that my y is going to be represented by my cost, since that's the dependent variable, and my x is going to be the miles that's driven. So when I set up ordered pairs from this information, if I'm going to drive 480 miles, it's going to cost me $380. And people tend to get those reversed when they set them up, but you've got to decide which one depends on the other one. So the miles driven is not going to depend on the cost. The cost is going to depend on the miles driven. So here's 780, and that's going to cost $440. So once we have two ordered pairs, we can pretty easily find the rest of this. For a linear function C that models the cost of driving, we're going to need to first of all know our slope. So if we do y2 minus y1 over x2 minus x1, we do that calculation, we're going to get 0.2 for the slope. Okay, so we don't have a y-intercept, so we can go back to the y minus y1 equals m times x minus x1. So we'll have y minus, choose either of our points. So I'm just using the first one here. So I will simplify this. And then I'm going to move the 380 over with the negative 96. And I get 284. Okay, so this is basically my model. I do want to replace this y with the c of x. It would be fine if you left your slope as 1/5, that would be fine as well. And this is 284 here. So at what rate does Lynn's cost increase for every additional mile she drives? So it's asking for rate. So it's essentially asking me for the slope. So it's asked my rate that it cost is going to be 0.2, and my y's are being measured in dollars, and my x's are being measured in miles. So it's costing me about 20 cents per mile. Okay, and so this is it written out in using the fractions. And that takes us to the end of this section. Please let me know if you have any questions.